Welcome back to CS395. This is Nihal speaking, and this week we are going to be talking about format string vulnerabilities and Ghidra. So Ghidra is an awesome reverse engineering tool. It was created by the NSA and their website is right here. You can download a zip file straight from that website, extract that zip file, and just execute the program. And it's a Java program, so any computer that has the JDK installed should be able to execute this file. It's used mainly for static analysis, but right now there's currently a debugger being developed for Ghidra. And once that is incorporated into Ghidra, we'll also be able to debug the program and do some dynamic analysis as well. What Ghidra is great at is it can take assembly code and convert it into C pseudocode, and then it will show you the assembly and the C pseudocode side by side. The C pseudocode can be a little bit inaccurate. So if you're using Ghidra, make sure that you're looking at both the C and assembly. If you see something that seems a little bit off in the C pseudocode, chances are Ghidra decompiled it incorrectly, and you need to go back into the assembly and see like what's going on. So today we are going to be reverse engineering a file called bitflip. When I execute this file, it's going to say your goal is to flip the bit at this address right here. And it says we're only allowed to use our user input. So we can't just modify the binary or something or patch it. And it asks us to enter our name. So I am going to type in my name here. I hit enter and it says, hello there, Nihal. All right, so to open up this file in Ghidra, you're going to want to go into the Ghidra folder on your desktop. And then you're going to want to type in Ghidra run, and that will execute Ghidra. It's going to take a moment to load. Just give it some time. Once it's loaded, you go to File, New Project, Non-Shared Project, hit Next. The project name, you can put in whatever you want. I'm going to call mine CS395, hit Finish. Once we're inside of here, we're going to hit I, or you could also go to File, Import, and then click on bitflip and just give it a moment to import that file, hit OK. Hit OK again. Double click on the file. The dragon will pop up when you do that. Hit yes when it asks you to analyze it, then hit analyze. All right, so what we're going to do now is we're going to go into this functions tab right here. If you don't have this tab, you can go to Window and then Functions to open up that tab. Once we see this function tab is open, we're going to type in main. And then we're going to double click on the main function. And then we're going to click on the listing right here to show the assembly. So what's happening here is this is the main function for the bitflip binary. This right here is the assembly. And this right here is what Ghidra thinks the original C code looked like. So right here, we have an undefined variable called local9 that's on the stack. Local9 has been initialized to 0. Then we call this function called hello using the address of this local9 variable, and then we exit the program after we do that. If we double click on this hello function, we can open it up. So this hello function right here, we can see that there are a few printf statements. There's an fgets, there's some more printfs, and oh, there's the shell function that's right here as well. So if we open up that shell function, we can see that the shell function will execute a shell for us. So it's pretty clear that our goal is to get this shell function to execute. But the only way that the shell function executes is if this parameter is not equal to 0. This parameter is the same parameter that we gave into the program when we called it back here, or when we gave to the hello function when we called it. And this has been initialized to 0. So when we go into here, this if statement will always become 0 because it's been initialized to 0 unless we do something to change this parameter. Right here, we see that there's this printf saying your goal is to flip the bit at %p using only your user input. %p we're going to use the first parameter for %p, which is right here. I'm going to rename this variable as flip because this is the variable that we need to flip. And that way it makes it easier for us to read this code. Next, it says printf, enter your name. And then we f gets in our name. So because we know that it asks us to enter our name, we know this variable right here must be our name. It must be a string containing our name. So I'm going to rename that to be name. This is not vulnerable to a buffer overflow because right here we have hex 32 bytes coming into the name buffer, but the name buffer has 64 bytes. I believe hex 32 is 50 in decimal. So because this is less than the total length of name, there's not going to be any buffer overflow happening here. Next, we have a printf statement saying hello there, and then we just print out our name. And then we check if flip is 0, and then we return if it's not 0. Or if it is 0, sorry. So the next thing that we are going to be doing is we are going to be opening back the slides again. And right here, there's an explanation of what format specifiers are in case you don't know. Format specifiers are used by the printf family of C functions. So if you think about printf, fprintf, sprintf, snprintf, all of these functions are vulnerable to the format specifier vulnerability. A format specifier basically tells the compiler to print off extra parameters that are on the stack. So if we do printf %d10, what's going to happen is 10 is going to get pushed onto the stack. And then when the printf statement sees this %d specifier, it's going to pop off 10 from the stack and then print that value out. So whenever we use a format specifier, we are essentially pushing things onto the stack and then we're popping them off the stack. So right here in this example, age and name are going to be pushed onto the stack. Age is going to be pushed first and name is going to be pushed last. It's going to print out my name is %s. And when it sees this %s, it's going to pop name off. Then when it sees the %d right here, it's going to pop age off. So these right here are some of the most common format specifiers that you see. You probably already know about most of these. %s will pop off the value off of the stack and interpret it as a character array. And then it's going to print off every value in that array until it sees a string terminator. %d and %f will interpret them as numbers. %x will also interpret the value on the stack as a number, but it's going to print out that number in hex. %p and %n are the most important. These two are basically what allows us to do the format string vulnerability. %p will print off pointers from the stack, and it will print out the pointers in hexadecimal so that we can see what those pointers are pointing to. And %n will pop off a value off of the stack, and it will interpret it as an integer pointer. And what it will do is it will print out the number of characters that have been printed out to that integer. So in case you didn't quite understand what that means, I have an example here where I use the %n format specifier in a very simple program. So what I did is I created this test.c program, and inside of the main function, I said int n equals 0. Then I had a printf right here that contained 38 characters, not including the %n at the end. The string in total is actually 30 characters, but it's only going to be 28. And sorry, I think I said 38 earlier, 28 characters because we're only going to be considering characters that get printed out. And since this %n right here does not get printed out, we're not going to consider that as part of the string. So what we're going to do is we're going to pass in the address of n, and then we are going to print out the value of n. So as you can see down here, when we look at n and when we look at the value that's in n, it's going to be 28 characters because those were the total number of characters that were printed out to the screen. A fun fact about the %n format specifier is it makes the printf function Turing complete. So that means %n lets us write to any memory, and the other printf format specifiers let us read memory, which is a really cool fact about the printf function. Anyways, if we use a $sign in our percent formatter, or sorry, in our string formatter, it's going to actually specify which value on the stack we want to pop off. So normally, if we just did %d, it would print out 1 in this example. But if we do %2 $d, it's going to print off 2 instead of 1. So it's going to grab the second value on the stack and print that off. If we do something like %4 $x, it's going to print off the fourth value on the stack, which in this case, it's x90. So this is just another example of me running a test program to show you guys how this works. Here I use %5 $d, and as you can see, 5 gets printed out because it was the fifth value on the stack. So for format string vulnerabilities, basically the way they work is whenever we have something like this, where one of the printf functions has directly printed out an input buffer, this is what causes the format string vulnerability right here. Whenever we see this line right here, we know that we have a format string vulnerability. The reason why we have a format string vulnerability is, let's say we control this buffer right here. And let's say whatever we type in gets stored inside of this buffer variable. If we type in %p, then this gets interpreted as printf %p. And even though there's no other parameters coming in here that are going into the printf function is stupid, and it will still print off stuff that are on the stack. So what'll happen is it will see this %p and it'll pop something off of the stack, but it doesn't know what's being popped off of the stack. It thinks that this was meant to be popped off of the stack, but whatever is just on the stack is still going to be printed out. So if we're in a situation where we can't look at something through a debugger, this allows us to leak memory off of the stack and see what's on the stack. So what we can do is we can send a bunch of %p format specifiers to the program, and it's just going to print out a bunch of values that are on the stack. The way that you would avoid this vulnerability is by using printf %s and then the buffer. You would not print it out directly like this. You would print it out using the %s format specifier. The reason you do it this way is because when we use the %s format specifier, the printf function will ignore any other format specifiers that are inside of the input buffer, and it will just make sure that none of the format specifiers in there leak memory off of the stack or allow us to write to memory. All right, so now I'm going to show you how you can leak memory off of the stack and how you can use that to even exploit a program. So I'm just going to close out a Ghidra real quick. I'm going to go back to the bitflip program that we were executing earlier. And actually, let me show you something in Ghidra really quick. Give me a moment. There we go. So right here, this is where the format string vulnerability occurs. It occurs when we input something into this name value right here. We input up to 50 bytes into there, and we just directly print that out without using the %s format specifier. And this is a problem. So to avoid this problem, or sorry, yeah, to avoid this problem, yeah, we need to use the %s format specifier. But if we would like to exploit this, then what we could do is we could write in %p period, and we could just write that in there a bunch of times. So what's going to happen is it's going to print out values that are on the stack, and it's going to print out periods in between each value on the stack so that we can see which values are located where on the stack. If you notice, we see that this value right here is equal to this value right here. So this value right here is the 7th value on the stack. We know this because if we count up, we get 1, 2, 3, 4, 5, 6, 7. So this is the 7th value on the stack. And what we can actually do is we can actually change what's here in this value using the %n format specifier. So earlier I mentioned that the %n format specifier will print out the number of characters that have been written out through printf, and it'll print it out through this value right here. It's going to interpret this as an integer pointer, and then it's going to print out the number of bytes that have been written out. So what we're going to do is we're going to have 6% Ps, 1, 2, 3, 4, 5, 6. This will pop off 6 values from the stack. And now we have this value right here that's on the stack. And we are just going to write out something to that value. And then we're going to hit enter. And as you can see right here, we get our shell executed. So in case you're still confused as to what just happened, our format string specifier just went in through this printf statement right here. This printf statement became printf %p, 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 %n. When it does that, it's going to pop off 6 values off of the stack. And then the 7th value is going to be this flip character right here. It's going to write to that flip. It's going to write to that flip pointer, and it's going to write the amount of characters that have been written, that have been printed out on the stack. And since that is not 0, this is no longer, this is now true. And then this shell function does get executed because of that. All right, so a shorter way of exploiting this program would be to use the $sign that I mentioned earlier. So what you would do is you could just directly print out, or sorry, directly write to the 7th value on the stack. And the way that would work is you would do 1% $7 $n. And as you can see, we still get a shell when we do this. So in case you're wondering why I put 1 in front of here, the reason I put 1 in front of there is because if I did not put in 1, if I just put in $7 $n, notice that it does not print out anything. So what's going to happen is 0 is going to be stored at this at the 7th value on the stack. And because 0 is being stored at the 7th value on the stack, this if statement does not become true, it becomes false because it is going to be equal to 0. So that's why I printed out 1 so that instead of having 0 being printed out there, it would print out 1. In case you've forgotten what the $7 $n thing means, it basically means print out or pop off the 7th value from the stack and use that value instead. All right, so for your homework, what I want you guys to do is I want you guys to practice exploiting format string vulnerabilities. And specifically, I want you guys to submit a write-up for the assist1 binary. That's going to be our first assignment. And keep in mind, this assignment will require that you use the / in front of the $sign symbol if you're using that. So if you're executing the binary like this, you would need a / in front of the $sign because you're putting this as an input argument to this program right here. Also, don't forget that %n saves the number of characters printed out. So if you want to store an exact value like 50, then you just need to print out 50 values before using the %n specifier. I'm going to show you what the homework looks like real quick. The homework is this binary right here. When you execute it, it asks you to give an input parameter right here. So just type in your name or something. It says, hi, Nihal, you currently have a 0% on this assignment. My gradebook is located at, and then it gives you this address right here. If you get 100% on this assignment, maybe I'll give you a shell. So what you have to do is you have to use a format string vulnerability to exploit this program and get exactly 100% on this assignment. And that is your homework. You're going to write a write-up for that. And I also want you guys to reverse engineer the program using Ghidra and to include some screenshots of you opening up the program in Ghidra inside of the write-up. All right, that is all that I have for you today.